All right, so just picking up where we left off yesterday, the last thing we talked about was Chapter 7, talking about work and energy. So Chapter 8 is where we started talking about linear momentum. Momentum, mass times velocity, it's a vector, it has direction. The importance of momentum is it is related to Newton's second law in force net is equal to change in momentum over change in time. So if you have something with a lot of momentum, it's either going to take a lot of force in a short amount of time or a smaller force in a longer amount of time to make it stop. Or if you have something stopped and you want to give it momentum, same thing. This is important in things like, your car has seat belts and airbags. The whole purpose of these devices is to decrease the force that it puts on your body when it brings you to a stop in the unlikely case of a collision. And so in that case, we take Newton's second law and we put sum of momentum, or change in momentum is equal to the net force multiplied by the change in time. And all of those devices, the airbags, seat belts, are designed to increase the change in time. The change in momentum stays the same, so the net force is going to drop. Now, with momentum, we can look at this equation and we see momentum is conserved. That means momentum does not change. Some people wrote in the test momentum is zero. That's not what conserved means. Momentum does not change if either the net force is zero or the time is zero. And it seems kind of trivial to say the time is zero. Nothing can change instantaneously. But when we're doing collision problems, we use the fact that the time for a collision is very short in typical collisions, and thus the momentum is essentially conserved during the collision, not before the collision, not after the collision, but during. And so that delta t equals zero aspect is actually an important part of our calculation of conditions where momentum is conserved. So you should be able to do conservation of momentum problems, that is, identify why momentum is conserved or why it's not. And if it's conserved, then momentum before is equal to momentum after. Now, center of mass, we didn't spend much time on that. So you're not going to have to do a calculation on center of mass, although you do need to know the center of mass is the place where you could treat as if the force of gravity is acting on. Collisions in one dimension, elastic and inelastic. We had a question on a previous test about what an elastic collision is. And an elastic collision is not defined as a collision where momentum is conserved, because we said as long as the collision is short enough in duration, momentum is conserved whether it's elastic or inelastic. Elastic collisions are collisions where the kinetic energy after the collision is the same as the kinetic energy before the collision. So in that case, you have the condition 1/2 mv squared 1 plus 1/2 mv squared 2. That's conserved in an elastic collision. And we worked out in class how we can go I should have put initials there and there. How we can go from that equation, conservation of kinetic energy for an elastic collision, to a much simpler equation that's V1 final plus V2 final is equal to, V1 initial plus V1 final is equal to V2 initial plus V2 final, if I remember it correctly, by using the condition of conservation of momentum. So you should be able to go through that work to show that if it's an elastic collision, and like I said, I think it's V1 plus, V1 initial plus V2 final is equal to V2 initial plus V2 final. You should be able to go through and show that that's the case for an elastic collision. Inelastic collision, well, technically an inelastic collision is any collision where kinetic energy is not conserved. But for the purposes of general physics, we limit this to the extreme case of the inelastic collision, which is when they stick together. So inelastic collision, the final speeds of the two objects are the same. So in a football play, when the defender makes a good form tackle, wraps up the player, they stick together, and that would be an inelastic collision. When you have a poor tackle attempt where the defender comes and just tries to blast the ball carrier, bounces off, and 30% of the time the ball carrier doesn't go down because it didn't get tackled, that would be elastic-y. It's not perfectly elastic. Obviously, the player deformed a little, which took some energy away, but that's closer to the elastic case. Finally, we had rocket propulsion. I'm not going to ask you to use the equations with rocket propulsion, but you should know, for instance, what is the principle that allows us to have a rocket in the vacuum of space actually work? Ruh-roh. Remember I showed you the newspaper article from, was it the New York Times, where they had the editorial that had said that it's not possible that students in high school physics around the nation know better than Goddard with his crazy idea that a rocket would work in outer space. And then they published the retraction as they were actually sending the astronauts to the moon. Rockets work because of conservation of momentum. The rocket is the same idea as me having this ball, and if there's no friction, if I throw the ball that way, I'm going to go the other direction because momentum is going to be conserved. And these same ideas apply to simple things like a gun. Anyone that's used a gun knows that the gun will have a recoil. The bullet goes that way, and the gun goes this way. And so you see those funny pictures of somebody holding a scope up to their eye and not having the stock on their shoulder. If somebody actually did that and fired it, it would take their eye out, right? Because the scope would just nicely poke the eye out because the gun comes shooting back when you pull the trigger. That's why that stock should be on your shoulder, so your shoulder can absorb that and stop the gun stock. If it's out in front of your shoulder, it'll get some speed and hit you with speed, and then it'll stop and hurt. Chapter 9, statics and torque. So this is where we learned our conditions of equilibrium. What are the two conditions of equilibrium? And equilibrium means equal forces. So those really are the defining characteristics of equilibrium. So how do we identify if a case is in equilibrium? Well, if the net force is zero, we know from Newton's second law, the net force is equal to mass times acceleration. So that means acceleration is equal to zero if it's in equilibrium. And likewise, from Newton's rotational version, the sum of the torques is equal to I alpha. And so if that's equal to zero, then alpha has to be zero. So if you have something that has a constant velocity, its acceleration is zero, and thus you satisfy the first condition. If the rotational rate is constant, then alpha is zero, and it satisfies the second condition. So a car driving down a straight road at constant velocity is in equilibrium. Now, if you take a statics class, engineering students, and if we have any, if you are taking the statics class, engineering class, statics means stationary. So the velocity is zero and the angular velocity is zero. As long as those are constant at zero, that's also equilibrium. And so statics class is a class entirely devoted to just doing what we did in chapter 9. That's what statics class is. So if you're an engineering major, you do a whole semester on this one chapter. Obviously, they get really into it. They do things like they take a bridge, and the bridge has, 70 pieces, and they calculate using some of the torques is zero and some of the forces is zero, what the tension or stress is on each of the members. It's a really complicated process. And so that's why they spend a whole semester on it. So force, we've already learned force is anything that pushes or pulls. That should be just second nature to you. Torque is the rotational equivalent. So it's anything that is putting a rotational force on an object. So I just gave somebody my masses, but if I have, well, here's a lighter mass. If I have this out here, it's putting a force on my hand that's making my hand want to rotate about the shoulder. And so it's creating a torque. And that torque has the equation R cross F. What does cross mean? It means you're multiplying the perpendicular parts. Now let's make sure we're clear. What's the difference between what I've drawn with the three things I've written? Erika.
The top one is a cross and the other one's a multiply.
It's kind of tricky. That's not the answer, but it's what people tend to think. These are all exactly the same meaning. That's radius times force, radius times force, radius times force. What would make them different? What would make Erika's answer correct? Now the top one is the radius times the force perpendicular to it. And it has a magnitude, so I use the absolute value to show the magnitude of RF times sine of the angle between the two. The bottom one, if I put vector signs, it becomes a dot product. What's a dot product doing? Multiplying the parallel parts. And so the dot product is also called a scalar product because its answer is a scalar. It's not a vector. So I don't have to put absolute value sign. And it's equal to RF times cosine of the angle between the two. Now, one of these things is torque. Which of the three is torque? The top one. The top one is torque. So the magnitude of torque is the radius measured as the vector going from the pivot point to where the force acts, crossed with the force vector. That's the torque. The bottom one, if I change R to delta X, what's the bottom one? I hope that's what she said. Work. Work is force times the distance parallel. Now, we always said force times distance parallel. Here I have delta X, the distance traveled vector, dotted with the force. That's distance parallel times force. With dot products, the order doesn't matter. So it's the same answer whether F is first or delta X. With cross products, the order matters. R cross F is equal to minus X cross, R cross F is equal to minus F cross R. And so you have to keep that order straight, and you have to be able to use the right-hand rule. So just very quickly, the right-hand rule if I have A cross B equals C, my rules are very simple. I take the index finger of my right hand and point it in the direction of A vector. And then I orient my hand so while keeping that index finger pointing the same direction, I can bend my middle finger. And as some people did, I first started marking it wrong, and then I realized, no, you can use all three of those. I usually do in the cross product. So pinky and ring finger are fine as well. So you can bend your middle, ring, pinky in the direction of the second vector, and then the direction of your answer is the direction that your thumb points. This includes the fact that you have to keep your thumb perpendicular to both your index finger and your middle fingers, and your middle fingers go between parallel to the index finger and going all the way around the palm. You do not bend your middle fingers back behind the index finger. That's not part of the right hand rule. Right hand rule, not the left hand. Why does all this matter? Well, you need to get the direction of your torques correct. And so since torque is R cross F, R is in the position of A, B is in the position of B, force is in the position of B, and the torque is in the position of C. So make sure you can do those cross products. And then we have all of the fun problems you can do, like you have a crane, and they tell you that you put a counterweight mass counter here, and you have a force of gravity that acts some distance or at some point here on the bar, and then you have a load there, and they ask you, what is the tension necessary? You look at that and you say, okay, well, there's got to be a pin here holding this in place. So there's going to be a force there as well. And I have to sum the torques acting on this horizontal bar. How do I know it's the horizontal bar? If I'm asked for the tension, how do I know I want to do the sum of the torques on the horizontal bar, not, for instance, the sum of the torques on the vertical bar? What? I want to make sure, I don't know what's going on down below at the base of the vertical bar. I know I'm going to have an upward force through the ground, sideways force. I don't know what's going on down there, but I know all of the forces except two here, the tension and the cross point. So it's going to be easiest for me to choose the horizontal bar. You could go ahead, you could work on doing the vertical bar, and you actually could solve it using the vertical bar. I just think it's easier doing the horizontal. So I would take this horizontal bar and I would say, before I get started, I must define my directions. X is to the right. Y is up. What direction does that make Z? Because it's a right-hand coordinate system, X cross Y is equal to Z. That's what right-hand coordinate system means. That's what we use in science. So X index finger, I have to take my right hand, orient my index finger in the direction of X. I now rotate so that my middle finger can point in the direction of Y and my thumb points in the direction of Z. So now I would sum the forces in, vertical direction, horizontal direction, sum the torques. Where would you sum the torques? Okay, you sum the torques about the hinge. Why would you choose there? Why does that make sense?
You can't sum the torques like for what you're solving for, and you know force of gravity, and but you don't know like force normal. It gets rid of force normal.
Well, the force in the hinge, we don't know what direction it is. We don't know what magnitude it is. We don't know what direction. We know it's got to have the tension is going to pull this way. So this is going to have to give a force this way. So the net force in the horizontal direction is 0. Actually, did I do that right? Perfect. I got to think about this some more. That's pulling that way. Yeah, some of the forces in the horizontal direction has to be 0. So if I look at forces that are acting on the vertical bar, this vertical bar has to be pushed that way, which means the bar is pushing this way. Yeah. So it's going to be to the right and up is the direction the bar is pointing on the vertical bar is pointing on my horizontal. Why did I get confused? Does anybody see why I got confused? I violated the rule of free body diagrams. That pink vector that I drew was not acting on my object of interest. And then I tried to take that and look at my object of interest and forgot which object it was acting on. So you have to pay attention to that. So I know I have forces like this, like that, and then like that and like that. And so all my forces there are shown. I don't know what the force on the hinge is. I don't know what the force of tension is. I can sum my torques about the place where the force of the hinge is acting, and then it will make no torque. So that's why Ashley correctly chose sum the torques about the hinge, because then there'll be no torque created by the hinge. I do have to know this height and this distance if I'm going to solve the problem. You have to have the right information, but summing the torques about the hinge would be the way to go. Which forces would make positive torques about the hinge? We can now use Ashley's favorite. Which forces would make it rotate counterclockwise is the same as which forces would make a positive torque. Well, I actually have three forces of gravity. Force of gravity on which thing? This one here actually is going to make it clockwise. That's a negative torque. The two that make a counterclockwise torque are this one and this one. And then the two that make clockwise torques, negative torques, are this one and this one. And so we would go through, use sum of the torques as 0, and we could solve for what that tension is. And once I know what the tension is, then I could use sum of the force in the vertical direction and in the horizontal direction to find what the force of the hinge has to be. So that's how you solve these kinds of problems. There's a fair amount of work with them, not a fair amount of complexity at our level. Then we got to things that were more interesting. Torque and angular momentum. I talked about this a little bit last class period just because, well, I wanted to. But this is where we actually have rotational dynamics. So we have our rotational kinematic equations. We have a rotational equivalent for Newton's second law. Our rotational equation for kinetic energy. So when we have something like a bicycle wheel rolling down the street, we say its center of mass has the translational kinetic energy, 1/2 mv squared, but it's also rolling, so its total kinetic energy is 1/2 mv squared plus 1/2 moment of inertia I times omega squared, omega being the angular velocity. And using that idea, remember we had the race between my brand new soup cans, and we found that soup cans that were identical in radius, identical in mass, did not go down the ramp at the same speed. Why not? Okay, the density. One had uniform density, the mass was distributed equally throughout. One had non-uniform density. When it starts rotating, you have the whole centrifuge idea. Centrifuge idea is that momentum makes things want to not go in a circle, makes them want to go in a straight line. And so things with more mass have more inertia. They go to the outside, so you end up with the more dense materials on the outside of the circle as it rotates. And that makes the moment of inertia, mr squared, larger because you have more mass on the outside and less on the inside. So the can that was chunky had different densities. More mass on the outside would make it so it has a larger moment of inertia, which means you'll have a larger percentage of the total kinetic energy in rotation, or a lower percentage of the total rotational energy in translation. It's going to be the slower one. So we can explain all of that using these ideas of rotational kinematics. Work done by torque was actually pretty simple. Just like the work equation, but now replacing force with its rotational equivalent torque, distance traveled delta x with its rotational equivalent delta theta. What does that dot between the two mean? You're multiplying the parallel parts. Of course, in our cases, we've usually done rotation where you only have rotation about one axis, so it was really simple. They were parallel. So in rotation, you usually have those are parallel, and it's real simple. Then we got to fluids. We talked about states of matter, the common states, solid, liquid, gas. Now, I will admit this. Trace asked me, well, he suggested, why don't you just put a question with a phase diagram on the test? And so I did. So if you didn't like that one, blame Trace. Feeling the pressure, Trace? The phase diagram I said was a PT diagram. PT diagram means you're going to put pressure in units of pressure. I put pascals in everybody's test, but atmospheres works as well. And temperature. And for normal materials, it went like this, where this line continues on. And over here is solid. And there is liquid. And there is gas. There were a lot of people that had which phase is which confused on the phase diagram. Remember, coldest temperatures, things freeze. So the solid is the farthest to the left. At higher pressures, you force things to go into more dense states. So liquid is a higher pressure state, gas is a lower pressure state. What do these dashed lines tell us? There's no question that it's a gas if it's within that piece. If you're a temperature above this temperature critical, then you couldn't tell the difference in a gas and a liquid. They're the same thing. They're one phase. And likewise, this dashed line here tells us the pressure critical. If you're a pressure above that, you cannot distinguish between a liquid and a gas. And so you could take and go from here to here. Okay, let's change color. If you have a process that takes something from here to here, it changes from clearly a gas to clearly a liquid without ever seeing a transition. The critical point is the highest temperature and pressure, so it's the combination of highest temperature and pressure, where you can have a distinction between a liquid and a gas. Down here, what was that thing? Triple point. The triple point is where you can have all three phases coexist. Now, this is for a typical material. Water is atypical. A lot of people put water instead of a typical material. What's different about water? For water, this line has a backward slope initially. Then in the end, it has to go forward again. And I showed you that there were many, many different phases of ice for water, not just one solid phase. That's atypical for water, but it's very important for our life on Earth, because that means that water, as you move up to higher pressures, it actually is more likely to melt. Instead of most materials, as you go to higher pressures, they're more likely to freeze. And, well, that's hand in hand with ice is less dense than water, so ice floats, so we form an insulating layer on tops of lakes so we don't freeze our lakes solid. Okay, so we have those common states of matter. What are a couple less common but still states that you see all the time? What kind of state do you have in not an incandescent, in a fluorescent light bulb? No recollection? The state of all matter in the sun. Plasma, right. The stuff that's in a fluorescent light bulb or the sun is a plasma. So that's a reasonably common state. Some people get really irate that we only talk about the 3 common states. They say plasma is another common state. Well, another one is a colloidal suspension. Most people, not counting me for the last 6 months, drink milk. Milk is a colloidal suspension. It's a suspension of little fat globules in water. And so that's another state of matter, and you can go on to other things. But these are the common ones. Pressure units, we have used all of these. What is a PA? Pascal. And in normal SI units, what would a Pascal be? Somebody, I heard Newton. Newton what? It's a force per area, Newton per meter squared. Of course, a Newton is a kilogram meter per second squared. So that's equal to a kilogram per meter second squared. Nobody ever writes kilogram per meter second squared, but that's what a Pascal is in base units. How about PSI? That's a pound per square inch. So that would be a libra per inch squared. ATM, atmosphere, with 1 atmosphere being 1.013 times 10 to the 5th pascals. And a torr. It's a torr, named for Torricelli. Also, it's called a millimeter of mercury because it's telling you if I have a mercury in a vacuum and I have this pressure of, let's say, 760 millimeters of mercury, that's 1 atmosphere, that the pressure on the outside will push my mercury up to a height of 760 millimeters in a tube. And so the conversion for that one is change in pressure is equal to rho GH. And so the H is whatever the number is for the torr. Rho is the density of mercury. G, of course, acceleration of gravity, gives you delta P in standard units. Pascal's principle. Pascal's principle says that if I have a confined fluid, if I increase the pressure one place, the pressure everywhere increases by exactly the same amount. And so that principle allows us to explain things like how a hydraulic lift works. A hydraulic lift, you put some load on top of a plate, and underneath that plate, you're going to have a fluid with a pretty big area. So the area there, of course, is pi r squared. And since pressure is defined as force over area, then the force is equal to pressure times area. And so if you have a big area, it doesn't take much pressure to have a force that's equal in magnitude to the force of gravity. You can hold it. If you have a small area, it would take a much bigger force. So by making that a big area, you can have a reasonably small pressure and raise and lower something like a car. Archimedes' principle had to do with floating. For Archimedes' principle, we had the weight of the fluid that is displaced, so that's density of the fluid times volume displaced times g, that's the way the fluid displaced, is equal to the buoyant force. So that was Archimedes' principle. And based on that principle, we could show that less dense things float on more dense things. Surface tension. Surface tension we did just a little with. Surface tension is like tension in a string, except for it's a two-dimensional surface. And so with surface tension, you have a fluid puts a force on something that is force is equal to gamma times the length in contact, where gamma is what we call the surface tension. So the force of surface tension is gamma times the length of contact. Now, there is one more thing to put into this. Force is a vector. If I put something really light on water, it's going to stay mostly above water, and the direction the water leaves is going to be largely horizontal. And so the surface tension force is going to be largely horizontal. And of course, I'm only going to care about the vertical component. And so you need to take this and say the sum of the force of the surface tension in the normal direction is gamma times L times sine of the angle between the horizontal and the direction that the fluid is leaving the surface. So you have to pay attention to direction there. And we talked about like the water strider, it's going to sink at the point where it's vertical. Because if it gets to vertical, then you have the full maximum surface tension is equal to its weight, putting more weight, and down she goes. And it won't come back up because it's not floating on the surface, it's surface tension holding it up. Flowing fluid. Fluid means it flows. So fluid dynamics is talking about things that flow. We talked about laminar, flows in layers. So it's smooth flow. And then we had turbulent flow. The Reynolds number, and you're not going to have to calculate a Reynolds number, is used to determine if it's going to be a laminar flow or a turbulent flow. The higher the Reynolds number, the more likely to be a turbulent flow. Continuity equation was something we spent some time on. Q is equal to, there's two ways of doing it, the velocity times the area, or you can have the density times the velocity times the area. And you say, wait a minute, those are going to have different units, right? Why do we have two and call them both flow rates? Well, for most fluids, the density change is negligible because we consider fluids to be non-compressible. They are. They have a bulk modulus that's not zero. But we consider them to be non-compressible, which means the density is the same everywhere in the fluid. And so then we just divide it out and say, well, here's, with the density removed, the velocity times the area is constant. And so that's just saying the volume per second that's passing is the same anywhere in a constrained system where you don't have fluid coming in or leaking out. And so we use that to say if I have something like this, clearly the area 1 is bigger than the area 2 because R1 is bigger than R2. What's going to happen to the speed as it goes into the bottleneck? What has to happen to the speed? It has to increase because the area got smaller and the flow rate's going to stay the same. Then we look at the Bernoulli relation. The Bernoulli relation says that there's a relationship between the speed and the elevation and the pressure. Specifically, the Bernoulli relation or Bernoulli equation says that pressure 1 plus 1/2 rho 1 V1 squared plus rho 1 GH1 is equal to pressure 2 plus 1/2 rho 2 V2 squared plus rho 2 GH2. This is very complete because I put rho 1 and rho 2. In everything you've done and probably everything you're ever going to do, rho 1 and rho 2 will be the same. So you'll just put rho, right? You don't need to put a subscript if it's the same. But what this is saying is, if you go from region 1 to region 2, the heights stay the same. So these two here, well, let me change colors. These two here will subtract out if you stay the same height. And so pressure 1 minus pressure 2 is equal to 1/2 rho, where I'm combining combining to say they're the same. One half rho times the difference in squared speed. It is important that you remember V2 squared minus V1 squared is nothing like V2 minus V1, the entire thing squared. It's a mistake people make from time to time. It's important not to. But that's going to tell us the difference in pressure. On which side do I have a higher pressure then? Do I have a higher pressure on the side where it is big and going slow, or on the side where it's small and going fast? The higher pressure is where it's going slower. When it goes faster, the pressure goes down. You might remember I told you my EMT teacher, who is like, you can actually look up on the internet right away. He is the head of the Golden Gate Division of California Highway Patrol. He had it backward. When he's talking about the body, the fight or flight thing, you have your veins constrict down. And you're saying, that's to make it so the pressure is higher in the artery. Well, the arteries constrict. So it makes the pressure higher in the arteries. No, it makes the pressure in the arteries lower, but it makes the pressure higher before the artery. And, he called me in class, and then I had to tell him he was wrong, and that's never what you want to do. Especially, as you might figure, somebody who's like the leader of the highway patrols doesn't like to be told he's wrong. So your body does that so that you'll have higher pressure further back, and you get more profusion back there where the higher pressure is, but you have lower pressure on the lower end. Viscosity. Had a question on the test I think most people nailed. Viscosity is telling us about the force between molecules. If you have a high viscosity, there's a strong force between molecules, so they don't flow very well. Low viscosity, very little force between the molecules, it flows really well. So water has a very low viscosity. It flows pretty well. We actually put surfactants in our water when we want to wash things, to make it so it has even less attraction to the other water molecules, so it can get into smaller areas and get grime out. And then we put polar molecules on one end and non-polar on the other, to lift the grime and separate it. So viscosity is something that tells us about how easily the fluid flows. And Poiseuille's law was the equation that tells us about how pressure changes due to viscosity. If I have water flowing through a pipe or blood flowing through an artery, because of the friction between the walls of the artery and the blood, I'm going to have a pressure drop as the blood flows through the artery. And Poiseuille's equation is the equation that allows us to calculate that. So Poiseuille's equation, I don't have it memorized. I have most of the equations we use in class memorized. That is not one of them. The pressure difference is equal to, it's got a fourth power of something, but I don't even remember what it is. But you should be able to identify, this is where that works, and use it if necessary. Then we got to thermodynamics, which is where we ended the semester, which is good because we only have 7 minutes left. We have 3 laws of thermodynamics plus the 0th law. Add them up, it's 4. 0th law is the one that says if object A is in thermal equilibrium with object B, thermal equilibrium, I have to define it before I go on. Thermal equilibrium was if 2 objects are in thermal contact, that means that heat can flow between them, and no heat flows between them, that's thermal equilibrium. That occurs if they're the same temperature, because the second law says that heat spontaneously flows from hotter to colder. So in essence, that's if object A is the same temperature as object B, and object B is the same temperature as object C, then object A is the same temperature as object C. That's the 0th law. First law, energy cannot be created or destroyed. Second law, we already said heat flows spontaneously from higher temperature to lower temperature, not the other way around. Now we have seen heat pumps that make heat flow as a net result in the opposite direction. but that's as a net result. In each piece of the process, the heat is flowing from hotter to colder. So a heat pump is not violating the second law. It's just manipulating. And then the third law is nothing can reach absolute zero. Absolute zero being the temperature where motion ceases to exist, or you asymptotically approach that. Quantum physics gives you a little fuzzy gray area there. So temperature scales, temperature is telling us about the average kinetic energy of the molecules. We have 3 scales. Which one is the go-to scale, the one that we use as our standard in science? We have 3 here: Fahrenheit, Celsius, and Kelvin. Kelvin. A lot of people missed points on the test because they forgot to shift to Kelvin. When is it okay to use Celsius? If it's a change in temperature. So if somebody wanted to get all persnickety, they could say that the Carnot efficiency can be written as temperature hot minus temperature cold over temperature hot. And they could say, well, I can use Celsius for these, right? What's the answer? Yeah, you can. But you have to use kelvins for this. Because the change in temperature in Celsius is the same as the change in temperature in kelvins. But that temperature that's by itself, the temperature hot, is going to be in Kelvin, whether you use Celsius or Kelvin for the change in temperature. Celsius scale, you should know the trivial fact, just because I think it's a cool trivial fact, that under Celsius define 100 degrees Celsius as the temperature for ice water, and 0 degrees Celsius is temperature for boiling water. But of course, that was flipped right after he died, right? Like within a year. And so 0 degrees Celsius is the temperature of freezing water. 100 degrees Celsius is the temperature of boiling water. Or so they teach you. What is inaccurate about what I just said? The what? Okay. What was inaccurate is, since the 1970s, they have changed the definition so that 0.01 degrees Celsius is the triple point temperature for water. And so that's the actual calibration point. Water still freezes at 0, but that's not the calibration point. It's 0.01 degrees Celsius. The triple point of water is the calibration point. And Kelvin scale is simply temperature Celsius plus 273.15. So that you have absolute zero is 0 degrees Celsius, or 0 degrees Kelvin, or minus 273.15 Celsius. Fahrenheit scale, forget about it. The only thing you need to know about the Fahrenheit scale is how to convert between Fahrenheit and Celsius. I'm not going to make you know that minus 40 Fahrenheit's the same as minus 40 Celsius. I'm not going to make you know that 32 Fahrenheit's the same as 0 Celsius, or 212 Fahrenheit's the same as 100 Celsius. Those are all true statements, but as long as you can convert, that's going to be the important part. Thermal expansion. With the exception of water and a very small number of other substances, what happens to a material as the temperature increases? It expands. Why does it expand? The temperature increases, that means the molecules are doing what? They're moving faster, which means their collisions are harder, which means they're bouncing off of each other harder, which spreads them out. Right? It makes perfect sense why things should expand when you heat them up, which makes it even more confusing with water, right? So we had both linear expansion, delta L equals L0. Oh boy, those do not look like L's. Alpha delta T, and volumetric expansion, delta V is equal to V0 beta delta T. On the test, you had a problem that was taken from the supplemental homework, but the supplemental homework did it wrong. It did it wrong, as many people did here. You have mercury, a liquid, in a tube that's constrained so the diameter stays constant. when you heat it up, what is increasing for that liquid? Its length or its volume? Okay, both are, but the only equation that's going to give you the correct answer is the volume, because it's expanding, it's trying to expand in all directions, but it's constrained so it can only expand in one. So the change in volume is going to be the area times the change in length. So that, because it was a liquid, you'd have to use the coefficient of volumetric expansion, and then we can calculate the change in length based on that. Ideal gas law, kinetic theory, yeah, we're out of time, but we have gotten to stuff that is recent in your minds. So I'll see you on Tuesday at, I believe,